Now let us move on to the quantum mechanics questions. So this question was asked in IIT Madras. So the question is like this. It starts from a simple question. Draw the wave function of a particle trapped in an infinite potential box at its ground state and first two excited states. So we all know what is the answer, how to draw it. So for ground state, it is like this, like this. And for this is ground state. And for first excited state is like this. Just remember this formula. Lambda is equal to 2L by N, where L is the length of the width of the box. Okay, for N is equal to 1, that is ground state, lambda is equal to 2L. For N is equal to 2, lambda is equal to N. For N is equal to 3, lambda is equal to 2L by 3. So we can easily draw this. Or you can simply draw this, like it can be simply visualized. Also, remember that for nth state, there will be n minus 1 nodes. Okay? For nth state, there will be n minus 1 nodes. See here, for here, n is equal to 1, right? So number of nodes will be 1 minus 1, 0 nodes. Here n is equal to 2. So there will be only 1 node. And for n is equal to 3, there will be 2 nodes. Okay? That's it. So the second question is like this. Now their probability graph. In the previous case, we have drawn the wave function of the particle in the ground state, first excited state, second excited state, when it is in an infinite potential well. Now they have asked to draw the probability graph. So simply what we have to do is, if psi is wave function, then the probability will be psi square, right? Mod psi square. So what we have to do is, if this is the wave function, and the probability curve will be same for ground state and for first excited state. Wave function is like this. We have to, if this is psi, suppose psi, this is psi 1, this is psi 2, we have to draw psi 2 square. Okay, then only positive side. Draw these things, curves, only in the positive side. And for psi second excited state, psi 3, the wave function is like this, just draw in the positive sides. So this is the psi 3 square. So then the professor asked like this. So you're telling me that we cannot see the electron, and the electron means the particle here. Electron at the center for first excited state. The entire width is A. Here it means A by 2. At this point, at this node, the probability is 0. So the professor asked like this. So you're telling me that we cannot see the electron at the center for first excited state. Yeah, because you have drawn like that, right? So, and is it weird? Does it seem to be weird that electron is present in this, within this infinite potential box, and it is moving within this infinite potential box, and at the central position, we cannot see the electron? How? So does it look absurd to you? So this is a question, this is a type of question that will be asked to you to confuse you. So this question was asked to my friend. She got confused and she said that she don't know the answer. But actually, if you think calmly, you will understand that if probability is 0, then it means we cannot see the electron, right? Mathematically, the probability curve looks like this. At a by 2, the probability is 0. It means that we cannot see the electron there. We have to stand at that point only. We should not get confused. We should not think if it is an electron, right? It is a particle. How can it be, it vanish at that position only? It is moving within this infinite potential box. Suddenly, how can it vanish at that central position? How can we not find a particle at a by 2 only? So we cannot think it like that, because in quantum mechanics, in the quantum world, we have to think about the dual nature of the particle. That is, the particle has a wave nature. Electron should not be analyzed on the perspective that it is only a particle. We should also take the wave nature, take its wave nature into consideration. Electron is both a particle as well as a wave. So electron, even though we think it as a particle, has a dual nature, which is particle as well as it is a wave, right? So it is possible that at a particular position, that wave has a 0 amplitude, which means the particle has 0 probability to be present there. So it means that, yeah, the probability to find a particle or electron at a by 2 is 0, which means you cannot see there. You should stand at that point. You should say it firmly when you're asked such questions. So the next question is like this, third question. What happens to the wave function of the ground state of the particle in a box when the potential is made finite? Okay. So the answer for this question, I think most of you will probably know. It is simple. If the wave function for ground state is like this, for infinite potential case, if it is made finite, if the potential is made finite, okay, what happens is that the particle's wave function tails into the forbidden region, like this. Like this. It tails into the forbidden region, which means at these positions, means within the region where the potential is finite V0, there is a finite probability to see the particle. So you have to say it like this. Kindly note here that the wavelength is increasing when the potential is decreased. That is, when the potential is made from infinite to finite, that is, potential is decreasing, right? The wavelength is getting increased if the width is maintained same. Width of the potential box is maintained same in both these cases. When the potential is made small, the wavelength is getting increased. Okay, you have to keep it in mind. So because the next question will be related to this. The next question asked is like this, fourth question. We are asked to consider 4 cases of particle in a potential box. First one is infinite potential case. Second one is left side is infinite and right side there is a finite potential of V0 to V02. And here also left side is infinite potential, right side is a finite potential, but V03, such that this V03 is greater than V02. Okay. And the fourth case is both sides we have a finite potential with equal finite potential V04. Okay. Now let us see the things. Okay. We are asked to compare the energies of the particle in the ground state for these 4 cases. So particle is in the ground state for 4 of these cases, but we have to find we have to find the order of energies for these particles in these 4 cases. So we can easily find it by using this equation. E is equal to h nu, right? So E is equal to h nu means we can write it like this, hc by lambda, which means the energy is inversely proportional to wavelength. Energy is inversely proportional to wavelength. We can take the wavelength as like this, lambda 1, lambda 2, lambda 3, lambda 4. Okay, compare these two things. Okay, first one and second one. Here, the width of the potential box is same for four of these cases. So here there will not be any tailing of the wave function into the forbidden region. So wave function, the wavelength of the wave function will be the smallest for the first case. So lambda 1 is first one, lambda 1. And here in the right side, there is a finite potential. So there will be some tailing. Left side, there will not be any tailing because potential is infinite. And here also, right side, there is a finite potential, but the finite potential present here is greater than which is present here. So the tailing will be small. So when the potential increases, the tailing becomes smaller. When it is infinite, the tailing is 0. Okay. Here, the potential, we have a finite potential at both these sides, right? Which means the tailing will be present here as well as at this end, which means it has the largest wavelength. This is the order. So the energies order will be opposite to this order because energy is inversely proportional to wavelength, right? So which means E1 greater than E2 and greater than E3 greater than E4. So this is the answer. This is the answer. Okay. Now let us move on to the second question. This question was asked in IIT Madras. So the first sub-question is like this. Draw the wave function of a harmonic oscillator in ground state and first excited state. So this is a simple question. You can answer it easily. Just draw it like this. For ground state, energy is not equal to 0. There is a particular finite energy for ground state as well. Energy is not 0 at ground state. And that energy is not a 0-point energy. So keep it in mind, okay? And so this is first excited state. Now, for your knowledge, I am also drawing the wave function for n is equal to 2. If this is n is equal to 2. Okay, this one. What you have to understand is that this height and this height should be equal. And these two heights, this one and this one, should be greater than this depth. Okay? Here also, this height and this height should be equal. And should be greater than this side and this side. Okay? The thing is, this side, I'm marking it as H1, and this is H2, H3, H4. Okay. Then H1 is equal to H4, H2 is equal to H3. Okay. Just keep it in mind. So here they have just asked to draw the wave function of harmonic oscillator for ground state and first excited state. So this is like this. So the next question will be the probability curve, probability density curve. So it is easy, just for ground state or for ground state there is no difference. For first excited state, just flip the part here to the upside. Okay. Then third sub question is, what happens to the wave function if on one side we have an infinite potential? This is a very important question. Okay, this is important. This will be asked in most of the interviews. Okay, so kindly study this, understand this. If you already know, just leave it. If you don't know, I will tell the answer. So here what happens if the wave function on one side is one side? So if we make one side infinite, potential infinite, and here in the right side it is normal, okay? So what happens to the wave function? So it is simple. We can see that. So what is a wave function of a harmonic oscillator? We know it is like this. Psi of x is equal to some coefficient into e to the power minus alpha square x square by 2 minus alpha square x square by 2 into nth Hermite polynomial of alpha x, where alpha is equal to square root of m omega by h cross, right? So here, as the potential at one side is infinite, it is essential that the wave function at this point should be equal to 0, because wave function should be continuous in nature. So wave function here is 0, right? Because here potential is infinite, so particle cannot exist here. The harmonic oscillator cannot come to this side, so wave function is 0. So to maintain the continuity, the wave function's value should be 0 at this point, right? So we can go to the next slide. So here, so as I said, the way to maintain continuity, wave function's value at this point, that is x is equal to 0, should be equal to 0. That is psi at x is equal to 0 should be equal to 0. So for the wave function's value at x is equal to 0 to be equal to 0, the Hermite polynomial Hn of x, n of alpha x at x is equal to 0 should be equal to 0, right? Because psi of x at x is equal to 0 if Hn of alpha x is equal to 0 at x is equal to 0. Okay, for wave function to be equal to 0, the Hermite polynomial and that x is equal to 0 should be equal to 0. So we know Hermite polynomials h0 of x is equal to 1, h1 of x is equal to 2x, h2 of x is equal to 4x squared minus 2. So you don't have to remember everything, you just have to remember that this Hermite polynomials at x is equal to 0 will be equal to 0 only for n as odd. Because for h0 of x, h0 of x equal to 1, whatever be the value of x, the Hermite polynomial is 1, right? Also here, even if you put x is equal to 0 here, the Hermite polynomial h2 will become minus 2, right? It cannot be equal to 0. So Hermite polynomial at x is equal to 0 can be only equal to 0 for n as odd. So this is the condition. So simply what we can say is that if the potential at one side is made infinite, it means that the wave function of the harmonic oscillator at that area is equal to 0. Because when potential is infinite, particle cannot go there, so it cannot be seen there, so wave function is equal to 0 at that. As wave function is continuous, as at the left side wave function is 0, at this point x is equal to 0 point, the wave function should be equal to 0, which means as wave function at x is equal to 0 should be equal to 0, that can only happen when the Hermite polynomial at x is equal to 0 is 0. And that happens when n is odd. So only those wave functions are possible for where n is odd. So which means only odd harmonics are allowed. Okay, so you have to answer it like this. So the ground state will be like this. We cannot draw the ground state of full harmonic oscillator, okay? Here the ground state will be like this, which this corresponds to the first excited state of a full harmonic oscillator. But for half harmonic oscillator, the ground state corresponds to this, okay, like this. And the second excited state is like this. Okay. At the end, the height should be greater, okay. Okay. Near the end, the height should be greater. Okay. This is how the wave function should look like. Now moving on to the next question. So next question is, what is the probability function for a classical harmonic oscillator? So this is a sub question of the previous questions, okay. So here, what is the probability function for a classical harmonic oscillator? So until now, what we have discussed is for quantum harmonic oscillator. So what is the probability function for a classical harmonic oscillator? You don't have to mug up the formula. Just think it. Just understand this. You have to say this to them. Okay. I usually in interviews in these institutes, like good institutes like IITs, IISc, IISc, good research institutes, Raman Institute, like these institutes, they will not expect you to remember the final formula. They want you to derive it in the sense you should know the basics. Like for classical theory, the fourth sub question is like this: what is the probability function for a classical harmonic oscillator? Until now, what we have discussed is for quantum harmonic oscillator. So their wave function and all comes. But here, for classical harmonic oscillator, what is the probability function? So when you are faced with such questions, they are not expecting you to remember or mug up the final formula. They expect you to remember the basics. So in classical theory, what have you learned? So for harmonic oscillator, you have learned that position is given, x is given by a cos omega t, right? Simply like this. So from here, what we can write is dx is equal to a minus a sine omega t, just differentiate it, into omega, right? Into dt, right? Now, what you have to understand is that for a harmonic oscillator here, okay? So it is, the potential energy is like this, right? Okay. And here it is energy. And here it is x. Suppose we are considering this particular region, dx, okay? Dx, this particular region, dx. And the time taken for the particle oscillator to move across this region, dx region, let it be dt, okay? Time taken by the oscillator to move across this region dx is dt. Then, and also assume that the total time period for the oscillator is capital T, okay? Capital T. So dt is the time taken by the oscillator to move across this region dx, and t is the time period of the particle. So now, probability for the particle to be seen in the region dx is given by dt by t, okay? So simply, the time taken by the particle to move across this region dx is dt, and the total time period is t. So the probability for the particle to be seen at this region dx is given by dt by t, the fraction of time taken by the particle to cover this region when compared to the total time period. That is the probability of the particle to be seen within this region dx, okay? That's it. So now we can write the probability as like this. So P of x dx is equal to dt by t, okay? Now we can substitute the value of dt from here, from this equation. From this equation, we can write what is dt? Just dx by minus A sine omega t. Okay, that is what dt is. So this is dt by t. Sorry that I forgot omega here. Here omega is there. Okay, omega. Okay, let me write it properly. Minus A omega. Minus A omega sine omega t. Okay. Now, moving to the next slide. Omega. Okay. So x is equal to A cos omega t. Then cos omega t is x by A. Cos omega t is x by A. Sin omega t is square root of 1 by x square by A square. Okay. Now we can substitute this square root of 1 minus x square by A square for sin omega t here. So what we get is probability P of x is equal to 1 by minus A omega t into square root of 1 minus x square by A square. Okay, so that's it. Now, if you have to plot the probability function, it is always like this. Okay, at x is equal to 0, if you put x is equal to 0 here, what you get is a finite value. So some finite value, okay? Some finite value. And at x is equal to plus A and minus A, what happens is, here you will get x becomes A, then 1 minus 1, which means 1 by 0. So it will become infinite. So at x is equal to plus A and minus A, the probability is becoming infinite. Okay? The wave function is becoming infinite. So that's it. So this is not proper, right? At x is equal to plus A and minus A, the probability cannot become infinite. So that is a drawback of classical theory for explaining harmonic oscillator. So now the next question is, the fifth sub-question is, compare the wave function for quantum and classical harmonic oscillator. So as I have already explained you, for quantum harmonic oscillator, it is simply like this potential curve, and this is the ground state, and this is the first excited state. Okay, first excited state, and also second excited and third excited state I have drawn to you, right? So here, so these are the wave functions of the ground state for ground state and first excited state for harmonic oscillator, quantum harmonic oscillator. So we can draw it explicitly. So here we can draw it like this. This is the wave function. It's I of x. This is for ground state, and this is for first excited state. Okay, first excited state, psi 1 of x, psi 2 of x. And now drawing the same thing for classical harmonic oscillator, we can say that. So here there is a like this. Okay, there is slightly some tailings. Okay, so let's see for classical harmonic oscillator, the wave it is like this. It is inverted, completely opposite, and there are limits minus A plus A. Okay, according to classical theory, the classical harmonic oscillator cannot go beyond these classical limits. The region outside this plus A and minus A are forbidden. They cannot go there. But here it is not there. There is a finite probability for the particle to exist outside of the allowed region. It can also go to the classically forbidden region. For this is for the ground state of classical harmonic oscillator. For first excited state, it looks like this X, and it is similar to like this. Okay, similar. So what you have to understand is that just when they ask like this, tell them that for ground state the wave function is like this. Draw them this, and for ground state classical harmonic oscillator is inverted. The probability is minimum here and the maximum at the plus or minus a points. For first excited state it is also similar. Here it is similar. Okay, and draw them these pictures. So it is very important to draw these pictures to them and say to them that here there is infinite probability for the particle to be present at plus a and minus a, because at plus a and minus a the probability is becoming infinite. Okay, and you have to understand that there is limits outside which the particle cannot be seen. For classical harmonic oscillator, there are finite limits plus a and minus a. Outside of this region, the particle cannot exist. According to classical theory, they cannot be seen. These are forbidden regions. These and these are forbidden region. But here, there is a finite probability for the particle to be seen outside, that is in within the forbidden region. Okay, outside of plus or minus and plus and minus a. So that's the main difference. So you have to draw it like this. That you like small tailings should be there, like this. Okay, like this you have to draw. So like this you have to draw, like this. Okay. So I think my drawing are not perfect. So I am providing you one good picture so that you can get the hold of the concept properly. So take the screenshot of this slide. You can understand it more. Look for n is equal to 0, that is the ground state. For quantum harmonic oscillator, it is like this. So there is some tailing in the forbidden region. But for classical harmonic oscillator, the probability is only present within the allowed limits. It cannot exist within the forbidden regions. So kindly see through this diagram. So I have explained the concept. You can understand by seeing these pictures. So as I have already said, the height of the wave function will be more near to the ends for quantum harmonic oscillator. So this red color denotes quantum harmonic oscillator. You can see this height and this height are same and greater than this height. So the height becomes more and more as you go to the near, which means that for quantum harmonic oscillator, the probability to see the particle is maximum at the turning points, near the turning points, except for the ground state. For ground state, the probability to see the particle is maximum at x is equal to 0, that's the central position. But for other cases, except ground state, for all other states, the probability to see the particle is more higher at the turning points, near the turning points. Okay, the probability for classical harmonic oscillator is more or less similar in all states. It becomes infinite at plus or minus a. You can see here it is similar, right? This one. Yeah, it is similar. So one more thing I want you to understand. Is that as n, the quantum number n, increases higher and higher, the behavior of classical harmonic oscillator and the quantum harmonic oscillator becomes more and more similar. So this is called correspondence principle. Okay, when the quantum number becomes more and more higher, very large, what we can observe is that the behavior of quantum systems becomes more and more nearer, or it resembles more and more classical systems. Here we can see that as n is 10, the wave function is becoming more and more similar to that of the classical harmonic oscillator. Take a screenshot of this picture. So it is very important. This part is very important because it will be asked in most of the interviews. You have to understand this concept. You have to know these things, what I have said now.